Hi everyone. So far we've discussed calculus formulas for arcsine and arctan, and in this video we're going to look at arcsecant. First up, we have the derivative of arcsec x. This one's a bit cumbersome because it has an absolute value, but notice that it also contains a difference of squares. So at least in that sense, this one behaves very much like the formulas we've already seen for arcsine and arctan. As always, we could state another formula which reminds us to use the chain rule whenever the argument isn't just an x. And now, if you forget about the absolute value for just a moment, we can now state a function whose derivative is 1 over u root u squared minus 1. According to the work shown here, that would be arcsec of u. As stated, we would need to assume that u is a positive number since we dropped the absolute value here. However, it's possible to account for negative values of u as well by applying the absolute value to the right-hand side as I've just shown here. If you want, you can prove that with a similar approach to the way we treated the absolute value with the natural logarithm in the past, but since it's not very enlightening, I won't bother showing all the details here. Rather than just u squared minus 1, it would also be useful if we could handle a more general difference of squares, such as u squared minus a squared. This formula works out to be 1 over a arcsec of the absolute value of u over a. So again, very similar to what we've seen with arctan and arcsine. All four of these formulas also can be proven using basically the same methods that we used for arcsine. So rather than repeating all the details, you can trust me that these are all true or convince yourself as necessary. Just make sure to put all of these on your formula sheet. With everything you've learned so far, pause and see if you can work out this integral. When you're ready to look at the solution, let's continue. The correct solution is motivated by recognizing that if all we had in the numerator was a 1, this would look a lot like the formula I just gave you for arcsecant. Unfortunately, there's also the pesky 2x squared in the numerator. So this motivates us to break up our fraction into two terms. Our first term would have a numerator of 2x squared, and our second term would have a numerator of 1. I've also applied the integral to each of these terms separately, which we know is valid when the terms are being added as they are here. Remember that the entire reason I broke up my fraction was because I noticed the second term looks like the arcsecant integral. And to make that more obvious, you could emphasize the difference of squares under the square root. This shows that the a value would be root 5 in this case. So according to the formulas given earlier, we can see this as 1 over root 5 arcsec of the absolute value of x over root 5. That takes care of the second term. But what about the first term? First, notice a simplification could be made by canceling x from the top and bottom. But what could we do next? Pause and think about it if necessary. The key here is to recognize that the numerator is the derivative of what we see under the square root. And a situation like this should make for a nice substitution. So we let u equal x squared minus 5, making du equal to 2x dx. So you can pause and check that this results in the integral of 1 over root u du. Now, what's the correct way to handle this integral? Well, make sure not to forget the basics. We need to think of this as u to the minus 1/2, and after that, we can just apply the power rule. That gives us 2u to the 1/2, and after that, the only thing left to do is put your answer back in terms of x, and you're done. Considering everything we've been talking about, it's important that you know every quadratic expression can be turned into a sum or difference of squares. It's just not always obvious how to do it. The method for doing that is called completing the square. Now, that's a topic you should have learned in high school, although I found a lot of students forget about it by the time they take this course. So I'll remind you of the basic idea and post another video which reminds you of the concept in more detail as well. Let's try it out. express this quadratic expression as a sum of squares, which is just another way of saying complete the square. The first thing to do is group the first two terms together in a set of brackets and leave the constant term outside the brackets. Next, we identify the coefficient of x, which in this case is 4. And once you've got that value, you're going to always divide it by 2 and then square the result. That probably sounds a little random, but that's the way this is always done, and I'll save a discussion of why that is for another video dedicated to this topic. So if we divide 4 by 2, we get a value of 2. And then if we square that result, we get a value of 4. And since the resulting value is 4, I'm going to add 4 inside these brackets. But I can't just add 4 without expecting to change the function. So I also need to subtract 4, which I'll do outside the brackets, to cancel out the change that I just made. If I do both of those things, adding and subtracting 4, then I haven't really changed anything. Now, outside the brackets, 20 minus 4 can be simplified to plus 16. And if you follow this process correctly, the part that's inside the brackets will always factor into a perfect square. In this case, we can see this factors as x plus 2 all squared, and the expression we see here is exactly the same quadratic function as the one we started with, but now we've expressed it as a sum of squares as requested. I'll reiterate that this process can be applied to every quadratic function. So anytime you see a quadratic function in an integral such as you see here, you have an opportunity to form a sum or difference of squares, and doing that might be the key to solving your integral. For the quadratic expression in this example, we've already done the work of completing the square, so you can just express it as I've just shown. And by doing that, you can see this shaping up to look a lot like the arctan integral, with u squared plus a squared in the denominator there. In this case, u would be x plus 2 and a would be 4. But remember that it's necessary to perform a substitution if we want to think of it this way. So don't forget to calculate du, which in this case is just dx. With that, we can represent our integral as 1 over u squared plus 4 squared du, which exactly matches the arctan integral formula with a equals 4. So we can declare this as 1 over 4 arctan of u over 4 plus c. Put your answer back in terms of x and you're done. So what does this example teach us? I've encouraged you to always be on the lookout for sums and differences of squares. So from this point forward, you should keep in mind that they might be disguised as quadratic expressions. Anytime you see a quadratic, you have an opportunity to complete the square, and that could likely reveal the structure which is needed for solving the question. So keep this tip in your toolbox from this point forward. Check in with me if you need any help reviewing how to complete the square, and I'll see you next time.